Welcome to The Explainer. Today, we're going to tackle one of the most beautiful and honestly surprising ideas in all of mathematics, conic sections. We're going to see how four shapes that seem totally different are really just different views of the exact same thing.
So let's just start with a question to get our heads in the game. Imagine you have a cone, like an ice cream cone, but it goes on forever. Now, what if you had two of them stacked tip to tip? If you took a perfectly flat sheet, like a knife, and sliced through that object, how many different kinds of curves could you possibly make?
Well, the answer is 4. And there are 4 shapes you see all the time. You get a perfect circle, the oval-shaped ellipse, the U-shaped parabola, and this wild two-part curve called a hyperbola. All of them come from this one simple act of slicing a cone. They're basically all part of the same family.
So how on earth does that work? Well, to really get it, we need to understand our starting point. And it's not just one cone. It's what mathematicians call a double cone. Looks a bit like an hourglass, right?
Here it is. All you do is take a straight line, that's the generator, and you spin it around a central pole, the axis. Where they meet in the middle, that's the vertex. This one simple object is holding all the shapes we're about to uncover. And here's the absolute key to everything. The whole secret is just the angle of your slice. The angle that your flat plane makes when it cuts through the cone is the only thing that decides which of the 4 shapes you're going to get.
All right, let's put this into practice. We're going to start with the simplest slices and then get a little more adventurous. First up, the shapes that close back in on themselves. So if you take your blade and slice it perfectly level, totally perpendicular to that central axis, you get exactly what you'd expect, a perfect circle. It's the cleanest, most symmetrical cut you can make. But now, what happens if we just tilt that slice a little bit? As long as the plane still cuts all the way through one of the cones, that circle gets stretched out. It becomes an ellipse. Think of it like a squashed or elongated circle. Now, this stretched out shape has this really cool property. An ellipse is defined by 2 special points inside it called foci. If you pick any point on the edge of the ellipse and measure the distance to both foci and add them up, that sum will always be the same no matter which point you pick. It's like pinning a loop of string at 2 points and tracing it out. You'd get a perfect ellipse every time.
And this shows you the basic anatomy. The longest distance across is the major axis, the shortest is the minor axis. And those 2 foci, they always live somewhere on that major axis. The farther apart they are, the more stretched out the ellipse looks.
Okay, so we've seen what happens when our slice is flat and when it's slightly tilted. But what if we tilt it to a very, very specific angle? A kind of magical angle.
If you tilt that slicing plane so it's perfectly parallel to the slanted edge of the cone, that generator line we mentioned, something totally new happens. The curve doesn't close up anymore. It shoots off to infinity. This open-ended curve is a parabola.
What makes a parabola special is its definition. It's all about balance. It has one focus point, but it also has a matching line called a directrix. And a parabola is simply the set of all points that are the exact same distance from that one focus as they are from that one line.
Just look at it here. Pick any point on that curve. The line going to the focus is the exact same length as the line going straight down to the directrix. It's this perfect equilibrium that gives the parabola its power, shaping the path of a baseball, the curve of a satellite dish, or the arc of water from a hose. All right, we've sliced parallel to the base, we've tilted it a little, and we've tilted it to be parallel to the side. What's left? Well, we can go even steeper. When you make the plane so steep that it's more vertical than the side of the cone, it can no longer be contained in just one half. It slices through the top cone and the bottom cone, creating 2 separate mirror image curves that fly apart from each other. This is a hyperbola.
The hyperbola, just like the ellipse, has 2 foci, but its rule is the mirror image. For any point on either of those 2 curves, if you measure the distance to both foci, the difference between those 2 distances is always the same. Not the sum, the difference.
And this is the result. 2 distinct branches, each one a perfect reflection of the other, curving away into infinity. This might seem like the weirdest one, but it describes the path of comets that swing by our sun and get flung back out into deep space.
So, we have these 4 shapes, all born from slicing a cone. It's a really cool connection in geometry. But you have to wonder, is there a single underlying mathematical rule that brings them all together?
Amazingly, yeah, there is. Every single one of these shapes we've just met can be described by this one elegant rule. It's a rule that relates the distance from a point on the curve to its focus and the distance from that same point to a line called the directrix. And the key is that the ratio of those two distances is always constant.
That constant ratio has a name. It's called eccentricity, and we usually just write it as E. You can think of E as a single knob you can turn. This one number tells you everything you need to know about the basic shape of the conic you're looking at.
And this is where it all clicks into place. When that eccentricity value, E, is somewhere between 0 and 1, you get an ellipse. When E is exactly equal to 1, that perfect balance we talked about, you get a parabola. And when E is greater than 1, the curve breaks open into a hyperbola. You see, they're not four different things. They're all just points along a single continuous mathematical line.
And that's what's so powerful. It shows that sometimes the deepest ideas aren't about finding something totally new, but about realizing that things we thought were separate are actually just different perspectives on the same beautiful underlying truth. What starts with a simple slice ends with a universal rule, and it makes you wonder what other hidden connections are just waiting to be found.